Hi everyone, I'm Hao Sun-Wen from University of Rochester. Today we are presenting a brief announcement, building fast recoverable persistent data structures with Montage. This paper is co-authored by me, Wentao Cai, Mingzhe Du, Benjamin Valpey, and Michael Scott. Non-volatile byte-addressable memory offers the possibility of keeping pointer-rich data structures across program runs and even crashes. However, building such data structures correctly is non-trivial. In order for a data structure to be recovered into a consistent state, the persistence of their operations need to be carefully ordered. But, since CPU caches are still volatile, stores in the cache can be evicted into NVM in arbitrary order. Consequently, the aforementioned persistence order need to be enforced with explicit write-back and fence instructions. Durable linearizability is the correctness criterion used by most existing persistent data structures and systems for NVM, which is straightforward but has high latency in every operation. The buffered version of durable linearizability reduces the latency on persistence ordering, but currently all the existing implementations of it are not general. Montage is the first general system that helps building buffered durably linearizable data structures. It persists operations at the granularity of coarse grain epochs. In the current implementation, two most recent epochs may be lost on a crash, as described later in this talk. It also further reduces the cost of persistence by only putting abstraction-related data in NVM, and metadata that are rebuildable from those abstract data will be recovered after a crash. Let's start with introducing rules of persist ordering. As an intuitive and widely used correctness criterion, durable linearizability, which was introduced in this conference in 2016, captures the idea that all operations precede a crash in linearization order should be preserved after a crash. Formally, a data structure is durably linearizable if it is first, linearizable, second, its operations persist before return, and third, their persist order matches their linearization order. To ensure the third point, for any operation O, all operation that it depends on should be persisted before O's linearization point. Otherwise, after its linearization point, O may get accidentally persisted out of order. Such order needs to be enforced by writing back and fencing on every happens before relationship on persistent data, which introduces significant overhead. Sometimes, however, we don't need persistence orders as strong as required by durable linearizability. Buffered durable linearizability, on the other hand, poses weaker ordering constraints which can lower the overhead on ordering. Formally, we define an era as consecutive chunk of history between two crashes. For every era EI, there exists a prefix PI of EI, such that for all possible I's, a history of all previous such prefixes tiling together, concatenated with the history since the ith crash, is linearizable. To ensure viable prefixes, if OX is persisted before OY, there cannot be a reversed happens before order between them, which shares the similar taste as the per operation stricter ordering of non-buffer durable linearizability. Buffer durable linearizability avoids the need to write back and fence each operation before return and on each happens before relationship, but it comes with the cost of losing some progress after each crash. Inspired by Dali, the first practice of buffer durable linearizability, Montage implements buffer durable linearizability by dividing era into epochs, which marks the persistence order of operations in batches. If two operations are ordered by epoch, they either do not have happens before order, or their happens before order is consistent with the epoch order. The epoch-based periodic persistence system of Montage is designed as follows. All write operations are assigned epoch numbers, which is read from a persistent slow-ticking epoch clock. In one write operation, all the writes to persistent blocks are marked with the same epoch number, so operations are linearized with epoch boundaries. This is important because the data structure is persisted in the granularity of epochs. If some updates of an operation are marked with a different epoch, the operation is not guaranteed to be failure atomic. However, it is totally fine for an operation to finish in the next epoch. Since read-only operations has nothing to persist, they don't need epoch numbers, but they are still linearized with other operations and can always find an epoch to linearize in. Before the epoch boundary from E to E plus 1, all operations in epoch E minus 1 are waited to finish and persist. If a crash happens in epoch E, the boundary between E minus 2 and E minus 1 is chosen as the consistent cut to drive the history back to. All operations in E minus E and E are discarded. Consequently, for those blocks last updated in previous epochs, they cannot be in place updated in the new epoch because the history of those blocks in old epochs needs to be preserved in case the new epoch is discarded. Instead, they make copies of those blocks and update the new copies. During this process, the data structure needs to make sure that the linearization order of operations is consistent with their epoch number. Specifically, if an operation sees some block from a later epoch, there might be an ordering issue. For example, as W1 and W6 overlap in time, it might be possible for W1 to linearize after W6, which is inconsistent with their epoch order. In such cases, Montage can optionally raise an exception as a reminder. In addition, Montage further reduces persistence overhead by reducing the amount of persistent data. Prior works like Nonblocking Persistent Memory Allocator RALOC, Persistent Data Structure Implementations MOD and Pronto showed that after crashes, data structures can be rebuilt from a set of data representing its abstraction. For example, the abstract data of sets and mappings can be their keys and values. For queues, it can be their values and queue node orders. For graphs, it can be vertices and edges together with their relationships. Montage allows data structures to only persist those data and helps iterate through those abstract data during recovery, so the transient indexing can be rebuilt. For a mapping, for example, this can be a linked list, a hash map, or a tree. On the other hand, in real-world scenarios like in-memory key-value stores, abstract data can take the majority of data structures' memory usage, which makes this strategy a preferable way to use NVM since it tends to be much larger than DRAM. Note that for queues and graphs, it is tempting to have persistent pointers as a part of abstract data, which may result in persistent chains of unbounded length. This can be troublesome because if one block is updated for the first time in a new epoch, it will be done out of place on a new copy with a new address. Then all persistent blocks pointing at it will need to be updated as well, and they may also need new copies. This chain reaction can potentially propagate to the whole data structure. To mitigate this, we can use sequence numbers instead of pointers to record the order of queue nodes. A more general approach for graphs is using relation nodes with multiple pointers pointing to the source and destination of original pointers so that the maximum chain length will be 2. As a glimpse of Montage's great performance, this slide shows the throughput of Montage among other persistent or transient implementation of hash maps. Montage has significantly better performance than all other persistent hash map implementations except Soft, which has a significant drawback that it keeps a copy of all data on DRAM, so the size of the hash map is bounded by DRAM capacity. For more information about experiment setups and results, please refer to the brief announcement and the full version of it. Montage is also suitable for non-blocking data structures. The challenge, in short, is that comparing to log-based operations, it is harder to guarantee non-blocking operations to linearize in the epochs they are assigned with. In non-blocking data structures, write operations need to be assigned epoch numbers prior to their linearization points. Meanwhile, epoch advance and further write operations in new epoch may happen concurrently, causing operations marked with older epoch linearized in the new epoch. So, if we want a non-blocking operation to linearize in a specific epoch, operations need to be aware of the epoch they should be in and to fail its linearization if the actual epoch is newer. To achieve this, Montage needs to identify all possible linearization points of all operations and make them epoch aware. If all data structure operations linearize on a double wide counted cast instruction, we can verify the epoch counter between the cast and the previous read. By doing this, readers are made visible to writers so that writers in an older epoch can never be linearized after a reader in a newer epoch. If good performance depends on invisible readers, we can use a software double compare and single swap or hardware transactional memory instead. This way, writers can check the current epoch number and try to linearize atomically without readers doing any updates. To wrap up, Montage reduces the persistence overhead of recoverable data structures by reducing the cost of persistence ordering and reducing the amount of persistent data. It is suitable for both log-based and non-blocking data structures. In experiments, it shows unprecedented performance as a general system for building persistent recoverable data structures. In the future, we wish to explore the possibility of non-blocking epoch advance and achieving atomic composition of operations on multiple data structures based on Montage. Thank you.